Welcome back, everyone. Today we're going to be doing the Sydney challenge for Microcorruption. We're just kind of coming back in after taking a little detour to set up a development toolchain for a real-world MSP 430. So let's dive right in. We're going to try to make this video a little quicker than some of the previous videos, now that we're kind of getting the hang of things. So let's have a look. Get our stuff all set up here. Everything looks good? Okay, so I clicked right through the window there. It basically was the same window that we saw in the first one. It didn't say anything new, except for that we were using a slightly different version of the lock. As I said, full disclosure, I have done this challenge before. It is sort of fresh in my mind, unfortunately. I really prefer when we can, kind of start these things completely from zero, but, we make do. This time I'm going to remember to start the clock. So the clock has begun. Let's do this. All right, so first thing we're going to do is reset our lock. And we're just going to step through it and just see exactly what happens here. So just type that in. It's going to send an automatic break when we return from that. And continue. And it says password is invalid. Try again. Okay, so let's reset it. And let's continue. Now, we have this break that we said that automatically happens when we come back from the user input prompt. So we don't really know where to go in the code right now. This code is actually pretty short. I could probably just scroll through and, oh yeah, look, right there. I didn't even know it was right there, but it's that close. But that doesn't really teach us how to find what we're looking for. So let's see if we can figure out where that code is. If this was a much bigger project, we would not have that ability. So let's check help, see what our options are. Remembering here we have solve and reset, continue step, step over next, step out, and finish. So step will continue the step until whatever function it's currently in returns control back to the calling function. So that's probably something really useful for us. I mean, right now we're only one step away from returning from whatever function we're in, but let's go ahead and use that F to pop back out of this function. And now we're in some kind of function called getSin. I don't know what get standard in, get serial number, I don't know what that means. Maybe that's something I'm supposed to know. I don't know, but I don't. Step out of that function. Now we're in a get password function. Okay, so now stuff is getting interesting. So that all makes sense, right? We were in the get password function where the password was input into the prompt. Totally makes sense. Return from this function, and there we see it. The next instruction to be executed is going to be check password. So we made it here as just like we wanted to. Great. So let's go ahead and step into that function. There we go. We'll set a breakpoint here for in case we have to come through this loop again. We'll just jump right here. We don't have to try to find it again. So let's see what happens here. The very first argument, we can try to take an overview look at this thing. So we see that the very last thing it's going to do is move R14 into R15 and then return. Okay. Along the way, it's going to make some comparisons and do some jumping. And it's even going to call itself again. Well, no, actually, it's going to call itself at an offset of 22 bytes and an offset of 24 bytes. So kind of looking at this, the very first thing we're doing, if we remember from New Orleans, the hashtag here, or as we older people like to call it, £, this hashtag here indicates immediate addressing. So immediate addressing is that actual value, 4637 in hex, is being compared to R15 at an offset of 0. We recall that's what the parentheses meant. That's something we had to learn in New Orleans. So the register R15 is in parentheses with a number next to it. We're talking about the offset. So let's look. What is R15? R15 is currently holding 439C, which is a familiar number from New Orleans as well, right? We saw that. So let's see what is in memory location 49C3. Wow, I'm really dyslexic. 439C. Is that what I said? So 439, and we counted across 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, and C starts here. So these 4 bytes correspond to the word test. This is all exactly what we saw in New Orleans, which is cool. All right. So those 4 bytes, so it's actually comparing, when it says compare R15, it means the byte at that memory location. So the byte at 439C is, my headphones always want to shut down on me, even though I'm talking into it. Okay, so it means it's that byte right there. So it's trying to compare, well, actually, that's not entirely true. Let's go look at the compare statement. No, I don't want Stack Overflow for this. One thing you have to be careful of when doing anything related to these existing challenges, and you get on like Stack Overflow, is you're real careful you don't hit somebody who is actually asking about the CTF and you get a direct answer to the problem. This kind of ruins everything. And if I was smarter, I would keep some tabs to these documents I find useful, or at least keep bookmarks. Okay, so the CMP, it's not on this one. Let's just find it on the page. All right, compare destination minus source and discard the result. What I'm looking for is whether or not this compare works on a single byte or a 2-byte group, because this is a 16-bit platform. So I think, I'm actually pretty sure that unless you specify cmp.b, which I don't, do they have that in this? I don't know if the, there we go. So they have the .b extension or the .w extension, which would indicate whether it's going to take a word, 2 bytes, or a b, a single byte. And I'm pretty sure, just on the behavior I've seen on this before, that CMP is taking a 2-byte word. So it's actually going to be comparing this for the very first byte of the test. After that, if they don't match, it's going to jump if not 0. You can think of jump if not 0 as jump if not equal. That's the easier way to think of it. I actually prefer when languages use the J and E version of it, but it means the same thing. We're going to jump if they're not equal off to an offset of 1C in hex forward. So 1C in hex, don't make me do hex math right now. But it's going to jump forward. I'm not going to follow it. But if it was equal, it's going to do another comparison. This time it's going to compare the direct immediate value 5530 with something that is 2 bytes offset from R15. So if we go back to what R15 is, 439C, and that corresponds to this word of data right here, and offset 2 bytes from that is going to be this word right here. Aha! So we have it. It's going to go through and it's going to check It's going to check the value stored in R15. It's going to check the value stored 2 bytes away from R15, 4 bytes away from R15. Then we're going to do something else. It's going to call check password again if it doesn't match. Oh, look, it uses J and E here. I don't know why it mixes and matches. That's interesting. I have to remember to look that up. Then it's going to move value of 1 into R14, and then it's going to compare another immediate value to the byte that is 6 bytes offset from R15. I hope I'm saying that right. I hope I'm saying that in a way that's clear. I gotta learn the lingo a little better. Then finally it's going to do a jump if equal this time. That's interesting. It's doing something different. And then we're going to clear R14 and then move R14 into R15. CLR means clear, right? I should probably just go back to one of the pages I already have open. Clear the carry bit. No, that's different types of clear. It puts 0 in the destination. That's literally all it does. Okay, this document is proving to be really useful. I've kept coming back to this one, and it's given me a lot of answers. I'll put the link to it in the notes. Let's see. So it's just an interesting thing that why would it clear 14 and then move 14 into 15? I guess it's just a trick of the assembler instead of just clearing R15 as well. Mysteries. So what we think we know right now is that we have this value and then this value. And I'm just putting them in here as a scratch pad so I don't put them in a notepad that you can't see. And then this value. This value. And this value. So it stands to reason that we could just take these values and put them in hexadecimal and see what happens. It might at least help us step further through the loop, or so let's try it. We're going to reset the lock, and we're going to continue. It also sets a breakpoint for us. I haven't mentioned it yet, but when you first run the program, it starts an initial breakpoint. That's at the entry point of the code. That is different than main. In New Orleans, you might remember that we set a breakpoint on main function. Main function is the start of your code. The entry point is the start of any preceding setup code that has to happen before the program actually begins to run. So the entry point is usually not a very useful place to start trying to find anything because it's not, the actual program hasn't started yet. So just a little aside there. So, oh no, we were going to put in hexadecimal those values and send it in, and let's start stepping. We're going to continue to get to our breakpoint at the beginning of the check password function, and then let's start stepping and see what happens. We compare and we can see that 0 is not set, which means they weren't equal, which means we're going to get the bad jump. Why did we get the bad jump? That's no bueno. Okay, so it took me probably about 15 minutes to figure this out when I did this challenge the first time myself. I kind of sat there, and when I figured it out, I didn't really figure it out. I tried something on a lark and it worked. Um, but that wasn't a good enough answer, right? If I'm going to be doing videos, I need to be able to explain it. Luckily, uh, the answer that we needed was actually, you could see it on one of the web pages that I was looking at um, during the New Orleans challenge, and I will post that right here. Um, but then also, upon talking about this challenge with a friend of mine, afterwards, I realized he helped me realize something that I didn't see before. So the problem is, the reason I didn't take that is because the MSP 430 is what's called a Little Endian architecture. So if you're not familiar with that stuff at all, it's something you really only have to worry about when you're dealing with computers at this level. It basically means that big Endian or Little Endian is when you, let's look it up. It's it's um it's the order that the bytes, sometimes the actual bits inside of the bytes, but typically it's the order that the bytes are in. When you're talking about a binary number, you have your most significant bit, which is the bit that changing it would cause the largest change to the number, right? So um, when it's written down, it would be the leftmost bit. That's the most significant bit. The least significant bit is the one bit, the one that you flip it and it just makes the number change by one. That's the least significant bit. Um, in a big Endian environment, the biggest byte is going to be the first byte represented, and the littlest byte is going to be the second one. In a Little Endian, that's reversed. So, oh, Wikipedia wants money. I usually do donate, by the way, but not right now. Although I'm sure all you would love to see a credit card number. So, yes. So right here, in a big Endian architecture, the number 1, 2, 3, 4 would be represented as 1, 2, 3, 4 consecutively. In a Little Endian platform, it would be 3, 4, 1, 2. And we can actually see this inside here. You didn't have to go out to Wikipedia or anything. This is what my friend helped me to see because I didn't even notice it. When you look at the way this line is represented, clearly, like, this is the actual, this is what the assembly gets broken down into, the actual hexadecimal values of that line. And so you can see, BF90 clearly relates to the CMP command itself. 3746 relates to 4637, and then 000 to 0. So we can see that Endianness right here. And I totally missed that my first time through. I never even noticed it. But when we were doing New Orleans, that's when I actually figured it out. I was like, oh, I see that now. So that's one of those things when you're learning, you can always go back and forth with you can always go back and forth. Redoing something can unlock new ideas for you. So that's cool. So if we go back to that string we had, and we just start swapping these things around. Let's try this. Let's reset the lock. Continue. Hex encoded. Send. Continue. Continue again. We had a breakpoint. And whoa, invalid password. Try again. Didn't see that coming. Did I do something wrong here? 3746 3055 4F53. Oh, I put 44 AC and I put this in there. That's not one of the bytes that's needed. Ha 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 ha. That was actually, that was just me going through it fast and not paying attention. I grabbed the value of the address location for the jump if not equal. To the check password function. I am silly. Brain stops working sometimes. continue. Access granted. There we go. Yeah, that was a silly thing on me. So now we can do solve. And there we go. We are in. Sydney's done, and we have unlocked Hanoi and Reykjavik. And we're going to hopefully get to do that video later today. And I might have somebody joining me to help me with that one. So I will see you all next time. Thanks.